definition. So we want to know the definition of a subgraph, and it's pretty evident what this definition should be. You know, there's substructures in all sort of categories of mathematics, but let's give a formal definition and then see a couple examples. So the pen. So a graph G prime is a subgraph of G. G is a graph. I won't always every single time specify that G is a graph. When we're talking about capital G in this class, it's almost always going to be a graph. So sometimes it's just a little redundant to write that over and over again. If we have the following properties, and they're very simple, that the vertex set of G prime is contained inside of the vertex set of G, and the same holds for the edge set. So the edge set of G prime is contained in the edge set of G. Those are the only properties you need, okay? Another way to think about this is a way to maybe construct a subgraph, is if you have a graph G, you can determine whether something's a subgraph or not if you can, you know, achieve the graph G prime, this is a G, by removing vertices and edges in some fashion to arrive at the graph here, right? If you remove vertices, you'll end up with a subset of the vertices. And if you remove edges, you'll end up with a subset of the edges here. One thing to keep in mind, and this comes up all the time in this class, is if you remove a vertex from a graph, it's implicit that the edges incident to it are also removed. They can't exist. They don't make sense anymore. So removing a vertex also kills all the incident edges. Removing an edge, though, doesn't destroy the vertices on either end, right? They may have reason to exist otherwise. Or if we can, remove vertices and edges to get G prime, then you'd say that G prime is a subgraph. Let's look at a couple simple pictures here. So maybe this graph here, say this is G, and then we can look at a, has subgraphs, s.g. I'll use for subgraph very frequently. This is a subgraph. Maybe this is a subgraph. I haven't drawn this one here sort of in the same fashion as this one here, but this is a subgraph because this vertex and these three edges correspond to this vertex here and these three edges, right? It's just a degree 3 vertex. That's a subgraph. Maybe one more to illustrate another concept here. Say that's also a subgraph, right? It's not connected, whatever that means, we'll see a little bit later, but that's a subgraph that actually uses all the vertices, but is missing certain edges there, okay? But let's do two that are not. So like the triangle is not a subgraph, right? If you look at this thing here, there's no 3 vertices that are all joined to each other by edges. It's just not there. You just have to figure that out by examination. And maybe another one that's also easy to identify. There's no vertex of degree 4 in there. So the graph made of 4 edges on a single is touching a single vertex. These are not subgraphs. Okay. So determining in general, like computationally, whether one graph is a subgraph of another graph is computationally difficult. It's not like a simple problem, but in practice, when we're working with things, we can reason one way or another that you have a subgraph or not through other means. But just writing software to do that, it's actually challenging. In fact, it's challenging to determine whether 2 graphs given as input are the same as one another, let alone whether one's contained in the other. But that won't be a real impediment for us in this class, okay? All right, so I want to use this subgraph notion. This comes up all the time in the class. Oh, maybe one more thing to emphasize too. By this definition here, it certainly allows the graph G is considered its own subgraph. Just like in algebra and all the other topics, you're a substructure of yourself. Moreover, the empty graph, that being the graph with no vertices and no edges, which we almost never will talk about, is a subgraph. Or maybe more interestingly, the graph of a single vertex by itself also is a subgraph, assuming the graph you started with had 1 vertex, which is a safe assumption. In fact, the graph of a single vertex is often called the trivial graph, and very often we don't even talk about that graph either, because I mean, what on earth are you going to prove about a graph with a single vertex? Like, there's nothing to say. Like, we know everything. So, although sometimes is the base case of an induction or things like that, it's worth thinking about. Okay, so I want to do something with this theorem here, this definition here, to actually find a certain type of subgraph. and we'll need another definition for that. I mean, this definition doesn't really need defining because it's obvious what it means, but the average degree so the average degree, let me check something real quick here. Anybody know how to see the participants list real quick? I'm worried someone might have joined here. Ah, I got it. Participants. Okay, good. Yeah, sorry about that. Okay, the average degree it's just the mean value of the degrees in the graph. So you add up all the degrees in the graph and divide by the number of vertices. That's all it is. Average degree is literally the average degree. So is mean degree value in G, okay? So we can actually define it computationally. It's usually defined as D of G. So remember, D of a vertex is the degree of that vertex. D of the graph is just the average across all vertices in the graph. So you could simply compute this by summing up all the degrees in the graph. V is a vertex in the graph G, and dividing by the number of vertices in the graph, right? That's literally how you compute an average in general. Oops. Come on. No. Oh my God. There we go. But why is this convenient? Well, the handshaking lemma tells us what the sum of degrees is, so we can simplify this a little bit further. This value here, the sum of the degrees, is 2 times the number of edges. That's what the handshaking lemma said. So we can rewrite this as the numerator is 2 times the number of edges in G, and to get the average, it's over the number of vertices in G. So actually there's like this very simple quantity here for the average degree. Average degree is always twice the number of edges divided by number of vertices. So this can be computed very quickly, assuming you know those 2 values there. Okay. All right, and so then the theorem that we're interested to prove here says the following, that if you have a graph G of a certain average degree, you can find a subgraph of it that has high minimum degree, which kind of makes sense, right? You can't have, the whole graph can't have really low degree and still maintain a high average degree for the most part. I mean, you can certainly have low degree vertices and then a bunch of high degree vertices and your average comes somewhere in between. But what I'm saying is that you can find a chunk of that graph whose all the vertices are relatively high compared to the average degree, okay? Which isn't obvious because if you try to pick it out vertex by vertex, you might find one part of the graph that's like really dense, has lots of edges, but unfortunately has a couple vertices of really low degree, okay? And so you're like, well, that's not good enough. I want all of them to have reasonable degree, okay? And you may have an idea how to solve that problem, and that will be the proof, but so let me state the theorem here, okay? So if G has average degree, D of G, just positive, so it can't be 0. If it's 0, this doesn't work. Then G has a subgraph H with minimum degree. So remember, we use lowercase delta of H for minimum degree. I hope I used that last time. Strictly greater than 1/2 of the average degree of G. Okay, so you can maintain that your resulting subgraph here has minimum degree. At least half. And this is actually really handy later on in the class when sometimes you know how many edges you have, therefore you have an idea about the average degree, but somehow you want to use a minimum degree condition. You want to be able to ignore really low degree vertices because they cause you some stress or some problem. And here you can say, well, the whole graph doesn't have high minimum degree, but there's a part of it that does. That's all nicely sending out a bunch of edges simultaneously. Okay, so just keep in mind the discrepancy here. This is the minimum degree. So in H, every single vertex has degree at least this quantity. And this is the average degree in H, right? So there may be low degree vertices, there may be high degree vertices. Okay, and so the proof is really quite simple. It's the first thing that you try, and it happens to work here, is I'm going to create a procedure here where I'm going to look at G, and I'm going to look for vertices whose degree is too low, and I'm going to remove them. So if I find a vertex whose degree is below that average, I'm going to throw it away. And then I claim that this procedure halts and gives me a graph H. So we just have to do a little bit of computation. This is a standard technique, not just in graph theory here. Okay, so what do we do to prove it? Remove vertices of degree at most 1/2 the average degree from G. So let's just do this one by one, okay? So keep in mind, as I remove a vertex, the degrees of other vertices drop at the same time. That vertex disappears. Right, let me just illustrate here. So say this vertex, it was in G, and it had low degree in this procedure, right? So I remove V. When I remove V, this vertex, these vertices here, their degrees also drop by 1 because they'll lose an edge, right? And so now when I do the second step of this procedure, the degree of this vertex may have dropped and it may have dropped below this threshold and become a candidate for removal. Okay, so I'll continue to do that. I'm not updating this quantity, but I'm updating the degrees. Okay, so this isn't a moving target. I'm always trying to stay above that, but the degrees themselves do potentially drop at each step, which is a bit of a worry. Okay, so remove vertices of degree less than, and I don't know, let's see, let's add like iteratively, okay? So you just do them one at a time, okay? So the key observation here is that this does not decrease the average degree of resulting graph, right? So if we do recompute the average degree at each step there, it can't decrease, right? You're taking a list of numbers that has some average and you're removing things below the average. What happens to the average? It can't go down. It might not go up, but it can't go down, right? So it does not decrease, okay? So what that means is that, well, okay, so that's the key observation, and eventually we stop, okay? So I don't want to say anything about the degree, but someone tell me, and this is a very simple question, why does this procedure stop? This is an important question that comes up constantly in graph theory. Why does this procedure have to stop? Like, forget about average degrees or anything. What's the totally trivial reason that this must stop?
Graph's finite.
The graph's finite, yeah. Remember I told you on that first thing that the graphs are finite. We'll use that constantly to guarantee that algorithms stop. If we have an infinite degree, then it's not, infinite number of vertices, then it doesn't clearly stop from this. And in fact, this procedure, I don't think in general you can guarantee it stops in an infinite graph, okay? So eventually we stop. So the issue is though, fine, we stop, but as Van points out, it's because it's finite, which means we might stop just because we like removed everything and then it's done. But the resulting graph there is not going to be any good, right? The graph with no vertices in it will not have the desired average minimum degree condition because it'll be 0, okay? So, but let's say eventually we stop with graph H. So let's talk about H for a second, okay? And without writing it out here, I claim that H has the property that's desired here. So first of all, can someone rule out the fact that we end with with no vertices? Like, why can't that actually happen? Why does the procedure actually not stop with an empty graph? It has to do with this observation.
Does it not have to do with the fact that, like, we're only removing things that are below the average? And like you said, that our average can never decrease.
Yes, exactly. That's it. Exactly, Sarah, right? So the average can't decrease. And we knew, actually, this is where we finally use this. The average was strictly greater than 0. So we're always above some 0 number at every step of the way. And so if you end up with an empty graph H, then this property had to have been violated because you got to 0 as your degree. But how were you at 0 when you were above 0 the whole time? Okay, so H is not empty. But more importantly, H has the desired degree condition. We stop at a graph G with minimum degree of H, is strictly greater than 1/2 D of G. And that's evident too, because if we didn't stop, there would have been a vertex of lower degree there to remove, but the procedure stopped. Why would it stop? Because there was nothing to remove. And that means that this had to hold for every single vertex. Every vertex had degree strictly greater than this guy here. Otherwise, we'd remove it and continue. But we know it stops. So when it stops, you have this thing here. Okay? Does that make sense? So it's actually like it's sometimes a little bit like surprising that you do this removal procedure and it like stops the way that you want it to. But if you just check the details against each other, It works out perfectly, and you get this nice subgraph. And actually, you could write a procedure to do this too, and it would accomplish exactly this. But we don't even have to do that. Okay. All right. So that was just the last little bit from last lecture that we didn't finish up. Really, I mean, the average degree and this theorem are quite handy, but what's really important is the notion of a subgraph. That's super important. That's something we talk about all the time, is when is something a subgraph? How do we find subgraphs? And so on. Okay. Now I can't, okay, this is weird. I can't move the canvas. All right. Okay. All right, so now I want to move on basically to the second section and talk about walks and paths and cycles and things like that. So we'll give a few definitions. They're pretty simple. Sometimes, occasionally, I will leave out or not clearly explain some notational details that are in the notes. If they're not clear, ask me. Most of the time, the stuff's just evident what I mean, I hope. But if it's not, just let me know. I don't want to copy out every single line from the notes, obviously. Okay, so a walk in a graph G it's a sequence of vertices, call them like x1, x2, up to xk, such that two consecutive vertices are joined by an edge. So walk is what you think. You start at a vertex, you walk along an edge to reach another vertex, then you walk along another edge to reach another vertex, and you continue to do this, and it creates just a sequence of vertices. Okay, so such that xi plus 1 is an edge of G. Okay, for, let's say, I equals 1, 2, up to k minus 1. You only have to go up to k minus 1, right? This is the last one, is xk minus 1 to xk. Okay, let me just emphasize, repeats are allowed. Okay, so walk is just a sequence. You might retraverse an edge that you already traversed. You might repeatedly see vertices in the list. Maybe, again, let's draw a picture. It's an easy concept, but this will be my sample graph for most of today. Let's name these vertices so it's easy to talk about a walk A, B, C, D, E. And we could have a walk W, which it could be, I don't know, A, B, C, then back to B, D, E, A, B, D, something like that. Okay, that's a walk. I don't know if I can replicate it, but you go from A to B, to C, back to B, down to D, over to E, up to A, over to B, down to D. That's a walk. A walk. There's many of these. When talking about a walk, I will often literally denote it in this fashion here, that we have W, and then this isn't really a sequence, right? I didn't put the commas in. It's like a concatenation of vertices, but when you read a concatenation of vertices like this, it just means that I'm going between these and the edges must be present. Okay. Something that's not a walk might include, like, the edge AD, which is not an edge, right? You can't walk along that edge there. Okay. So that's sort of an object in a graph. It's not technically a subgraph, right? Because we have like repeated edges, and it does kind of induce some sort of substructure, but we don't think of a walk as a subgraph. It's just some kind of procedure or thing that you can do in a walk, in a graph. Okay. So a path, it can be defined independently, but I'm just going to call a path a walk with no repeats. So is a walk without repeat vertices or edges. If you have no repeat vertices, you can't have repeat edges. Okay. So a walk could be, a path, could be, I don't know, A, B, C, D. That's a path, right? From A to B to C to D. Okay. Paths are also just a category of graphs. You can talk about a path with 10 vertices, with 3 vertices, with whatever. But you can also talk about a path is a type of subgraph of a graph. Okay. Let me add to this a little. So, yeah, the length of a walk or path is the number of edges, and counting, if they're there, repeats. So it's just the number of steps that you take in the walk. Very natural definition for the length, okay? I'm not going to write it out, but we call the end vertices of a path are just the starting and ending point here. So in this one, A and D are the end vertices of the path. Here, A and D are the end vertices. Okay. Okay, so very simple theorem here about paths and walks is that if you have a walk, oh yeah, let me actually add one more definition here. So a path or walk works for both with end vertices, say X and Y, is called an XY, well, path or walk, depending on which one you're talking about. It's just a shorthand notation. So if I'm discussing a path in a graph that specifically starts in X and ends in Y, although it's equivalent to starting in Y and ending in X, right? Remember, there's no orientation in the graph. Then we just call it an XY path for short. It just makes terminology very, very simple sometimes. Instead of having to say, let P be a path with starting vertex X and ending vertex Y, XY path. So, okay, so the theorem says, and this is not surprising, and you can prove it by a picture, that if you have an XY walk in your graph, so some way of walking along edges to get from X to Y, then you actually have a path. You can do it with no repeats, right? Like you can get from A to B without repeating if there's some way to get there, okay? So if G has an XY walk, then G has an XY path, okay? And just like intuitively, does someone want to shout out why you think that's true, or like how to say you had the walk, how do you construct the path? Just like roughly what would give you that? And then I'll show how we can formalize that. Like, why should it be true that if you have a walk that you have a path, like instead or something?
We can treat, on a walk, we can treat the repeats as like a loop, and
yes,
we just skip that loop.
Yeah, exactly. Just skip all anytime you repeat a vertex, so return to a vertex, like just skip ahead instead, right? You know, you went from A and then you took this detour, ended back at A, don't take the detour. So that basically works as a proof. You can say that, but let me show you a little technique here. And we'll use it in the next two proofs here. It's super useful in graph theory. This is one of my favorite techniques here. And I'm going to call it max, min, although it's even more general than this, substructure. Okay? Usually it's a subgraph, but we're going to look at a longest substructure, a shortest, or most edges, or most vertices, something in the graph that's, that's of the biggest type. It's really handy to work with. It's easy to get contradictions when you work with things like that, okay? So let's say we have the walk, and let W be a shortest. So when I say shortest, I'm referring to length. So I'll say shortest length now, but most of the time we'll just say shortest. Shortest length, XY path. Sorry, not path. I don't know that there's such a path. I'm trying to prove it. Walk, okay? So a couple things to emphasize here. We're given that G has an XY walk, right? That means that there might be many of them. We'll talk about that later. There could be many ways of getting from X to Y, but among all those paths, there do exist some of the shortest length. For each one, you can compute how long it is, and the shortest ones exist. Very important. I said A here, not V. I don't know that there's a unique shortest. There may be multiple shortest ones, but there certainly is one. And again, this doesn't even follow from finiteness, but there's a finiteness argument in the background here. There's only so many of these XY walks. Enumerate all of them, find one in the list that's shortest, okay? Very simple concept, but just adding this little detail here, shortest length, to if you just started with W that was not shortest length, you'd have to like prune it and shorten it by skipping repeats, and you might have to do an induction and say do it until it stops, and like that's a little informal. Here, just start with the shortest one. So my claim here is that the shortest one here is a path, and that's exactly, so let me write that. So claim that W is a path, actually, right? That's actually an XY path. And this comes from is it Andy? Yeah, what Andy said here is that, let me just write this out a little bit differently, but the claim follows as follows. If no repeats in W, well, then we're done, right? If there's no repeats, it's a path by definition, and we're done. So that's not the case we have to address. The case we have to address is that there's repeats. So otherwise, suppose we repeat vertices xi equals xj. Okay, so let's just think they're enumerated x1, x2, x3, x4, starting with x and ending with y, and somewhere along the list. So maybe we can even, let me just even add here. So just say that w is x1, x2 up to xk, and this x is the starting x, and this xk is y, just to give it a name there, okay? So say we have some repeat in the list there, that xi equals xj, even though we've given them sort of different names here, okay? Then, just skip vertices xi plus 1, xi plus 2, oops, and so on and so forth up to xj, okay? So in our list. So we go from x1, x2, eventually reach xi, and then we jump up to xj plus 1, and then continue from there, right? So this stuff that was in the middle got thrown away. But why does this make sense, right? Remember the definition of a walk or a path? That we always had an edge between consecutive vertices. Why do we have an edge here? I know I have an edge between xj and xj plus 1. Why do I have one between xi and xj plus 1? I know it's a dumb question, but
Aren't they the same vertices?
it's exactly. J and I are the same vertex. So there is an edge there. There's one little issue here with the way I've drawn this that actually is suggesting something that may not be true. Does anybody see, like, there's kind of like a little bit of a bug in this proof here? That it still works, but it's something we should be careful about. What if
It's unclear that that like I equals j is like not y, our final vertex.
Yes, okay, great, Van. Yeah, exactly. So it could be that xj equaled xk, and so that it actually ended at xj. And so when I write this xj plus 1, it doesn't, like, that there's no such vertex, right? But it actually doesn't, it's not a problem, because what I actually said above here is just skip these vertices or remove them. So it'd mean we reach xi and then we'd be done. The rest of the thing would be removed there. So what I drew here is illustrative, but it's a little bit incorrect. It's better to just stop at the proof here and just say, just remove those vertices. And then if you've arrived at xi, you don't need to make another step if xi is the last one, okay? This is a good, it's like just a good warning that when you make these assumptions, like you draw things like this, you're often like adding in for information that doesn't really exist. It doesn't change anything here. But yeah, if you just skip these things here, it's clearly, okay, oh, sorry, let me word some things. So just skip those vertices. I'm gonna delete this part here too, because I wanna, there's a punchline. Oh my God, it's slow. So just skip those vertices, and resulting is an XY walk. Okay, so what? What's the problem? So I found a new walk, but what's up with this walk?
It's smaller.
It's smaller, exactly. The resulting XY walk is shorter. And now is why we cared about having a shortest length path, because that's a contradiction. We started with the shorter and we shortened it under the under the condition that there was a repeat. We got a contradiction. So this is a contradiction, right? This little lightning bolt here. It's a contradiction, which means that this case can't happen. So the shortest walk was a path because there couldn't have been a repeat, okay? Again, the procedural way of removing things step by step is equivalent to this. This is just a little bit cleaner. And there are instances where a procedural argument is really hard to actually write. And it's like, wait a minute, let's just kind of pretend we're at the end of the procedure and work with the smallest or shortest or easiest example and prove that we can't get any smaller, okay? All right, so I'm going to give another proof of this type for a different thing. Why does this happen? Too many like clickable devices simultaneous here. Like it's, all right, let's see, I think I got it now. Yeah. All right, so, yeah, that's a max-min substructure argument. Ah, yes, we need another definition. I know I didn't put def every single time, but we need the definition of a cycle. So a cycle is very much like a path. Some books define it as a path plus the edge, the two vertices at the end are joined by an edge, which is true, but I think this definition is dangerous. So I'm just going to define it directly. So a cycle is a sequence of vertices x1 up to xk such that the xi, so a sequence of, this is important, distinct. Okay, there's no repeats in a cycle. Distinct vertices such that xi and xi plus 1 is an edge. I'll just put it like that. For I equals 1 to up to k minus 1, and xk x1 is an edge. If I wanted, I could have written this like modulo k or whatever, but it doesn't quite work out perfectly. Okay. Now let me draw a picture. What's a cycle? Looks like a path, except it goes all the way around. Okay, that's a cycle. Length is the same notion, number of edges. Okay, so length 6 cycle. Here's a length 3 cycle that we've already seen. Triangle is a cycle of length 3. Okay, very simple. Cycles are very interesting and very important in graph theory, both in applications and in theorems. And it's amazing, we don't even know everything about cycles that we should know, which is like crazy, because I mean, look how simple these things are. But anyway, we'll see some of them later on. Okay, so a graph G with minimum degree, let me say it in words too. Min degree G contains, okay, I didn't say this in the definition of subgraph. When H is a subgraph of G, so H is inside of G, I'll often say that G contains H instead of saying that is a subgraph of H. There's no real good reason to have both terms because they don't really shorten things, but it's just common parlance in graph theory. Okay, so graph G, I'll even say it this way the first time, contains as a subgraph, okay, I'll almost never say it this way from now on, but just to emphasize this first time, a path P of length at least the minimum degree. So you can always get a path of at least the minimum degree. If every vertex has degree 10, you'll find a path with 10 edges, no repeats. And as long as the minimum degree is not too small, so as long as the minimum degree is at least 2, if the minimum degree is just 1, your graph isn't very interesting and the second part doesn't hold. So if the minimum degree is at least 2, you also have a cycle of length at least delta G plus 1. Okay. So before we prove this, I'm going to do both parts separately, but why does the second case imply the first? At least when the minimum degree is large enough. Why does the second imply the first? So the second is that we have a cycle of length delta plus 1, and the first is that we have a path of length delta.
Like the first definition you presented of a cycle, which we're not going with, is like it's a cycle plus an extra edge. And
path,
so
path plus an extra edge.
A path plus an extra edge.
Yeah, exactly, right? Or if you look at the picture here, like this cycle here has length 6, and if I remove any edge of the cycle, I'm left with a path clearly between this guy and this guy, and the length has to be 1 less because we lost the edge that I removed there. So cycle always contains a path of length one shorter there. So this second condition, that we have a cycle of length at least delta plus 1, will give me a path of length delta. But the second part relies on this additional assumption, which is not a big assumption, but so it doesn't fully imply the first one because we'd have to deal with the delta equals 1 case above. I'll just prove them separately because the point here isn't like super efficiency in proof, it's the method. Okay, all right. I'll kind of give 2 arguments for the first part here, okay? So again, I want to use a max substructure type argument here. In the last one, we took a shortest walk. Here, I'm going to take a longest path in G, okay? So let, how did I write this out here? Yeah, let P equal x1 up to xk be a longest length path in G, okay? Like I said, whenever I talk about paths and talk about longest or shortest, I'm referring to the length, that property. So I'm like soon I will not use the term length anymore when talking about longest or shortest path. Okay. Its length, so length of P is k minus 1, right? Just because I gave the vertices names here, x1 up to xk, they're k minus 1 edges, right? The first edge out from 1, the second edge out from 2, the last edge out from k minus 1. So this k minus 1 edges, so that's the length. But that's just defining the length. This k doesn't mean anything yet. Okay, let's look at a picture. So here's x1, here's xk, and these are like the vertices inside. Okay, so longest paths are wonderful to work with because let's look at x1. There are other edges coming out of x. How many edges are coming out of x1? At least one, certainly from the picture, right? And even more from the what we know about the graph. It has a minimum degree delta g. So there's at least the minimum degree number of edges coming out of it. I don't know what it is. If it's 20, then there's at least 20 edges coming out of it. If it's 5, at least 5 edges are coming out of it. Where do those edges go? Can there be an edge from x1 like going out over here? Yeah, I see people nodding, but it's not. No, not Andy. Do you see why? I see you changing your mind here.
Because that would add on to, there'd be a longer path.
Yeah, yeah. So when I illustrated this, I meant that this vertex was outside of the path here, right? This is longer, right? This is longer. And we don't have that. We started with the longest path, which gave us this nice property that the edge doesn't go out. That doesn't mean there are not edges from x1. They just, any edge from x1 goes back into, oops, that goes back into the path. Does that make sense? They sort of go back in. There's already one going back in a sense, but they jump back like this. What about for xk? We can say the same thing. If it goes out like that, then it's a longer path. So all of them return. We don't actually need that property now though, okay? Because x1's neighbors, one of them is x2, and the other candidates are anywhere from x2 up to xk. So the neighbors of x1, they live among the vertices x2, x3, up to xk, right? Oh, this is a subset, not a less than or equal to, right? So the neighborhood of x1 has to live inside of this thing, otherwise longer path. Okay, but this thing here can give me some information because the minimum degree of g is bounded above, or it's, you know, the degree of x1, sorry, is at least the minimum degree, right? That's the definition of minimum degree. Every vertex has minimum degree, at least that. The degree of x1 is the same as the number of vertices in the neighborhood of x1. But the cardinality of this neighborhood is less than or equal to the cardinality of this set that it's contained in, right? So I guess I'll just, yeah, why not? We're still early, so I'm not gonna, later on I may not, you know, do all of these steps here, less than or equal to the cardinality of that set. The cardinality of that set is at least, I mean, it is exactly k minus 1, right? And so this long inequality here, I don't understand. This thing like works 50% of the time. I can't scroll my canvas again. Why? Now I really don't understand why I can't do it.
Do you have to select the little arrow key in the bottom right little tool circle?
I have a hotkey set up to work on my spacebar, but if maybe there is one here, I don't see one. Let me see if there must be just a pan option here.
Can you scroll with arrow keys?
I can't. I just tried that actually. It actually feels like. Oh, you know what? I could try here. Okay, that doesn't solve our problem, but I just wanted to make sure I hadn't reached the bottom of the file. How? Oh man. Crop, adjust, rotate, mirror, flip. No.
Are you able to scroll with the scroll wheel on your mouse?
I can't. No, that doesn't work. That zooms. This is
Oh,
massive.
okay.
Yeah. Okay, is that still pretty visible? I can do that just for now. Like we'll see if maybe I'll get details back. So, okay, so this inequality though, what is it established? The minimum degree here is less than or equal to k minus 1. What was k minus 1?
The length?
Yeah, it was the length. So we have a path of length k minus 1. We have a path of length at least the minimum degree, right? So this path here, p. So p has length at least delta of g. by the above inequality there, okay? So basically, you know, if you see this picture here, we had to have that happen because the neighbors of x1 had to go into the path, and so the path had to be like long enough to accommodate the neighbors because they couldn't go out, okay? So that ends the first part of the proof. Let me talk about like an alternate idea. Maybe I won't even write this out, but I'll just describe it. Again, there's a sort of procedural argument for making this work as well, and it's the following. Suppose I want to just actually construct a path, because notice this doesn't construct a path for me. This is a non-constructive proof. I say, take a longest path, and it's long enough. But where is it? How do I find it? I don't know. I just know that one exists. But you can construct one as well in the following way. Just grab a random vertex. I'll call it x1 for now. And then I haven't done anything yet, so let's walk out of x1 to x2. Okay, now I want to continue to walk and grow my path. So I can walk out to x3. Now things get a little trickier. I want to walk out from x3, but what do I have to make sure not to do? What am I not allowed to do?
Return to a previous
Yeah,
vertex.
I shouldn't return, right? Maybe this edge exists here from x3 to x1, so I don't want to take that. But if my minimum degree is high enough, I'm guaranteed some safe vertex, so I can walk to x4. Right now from x4, I have some unsafe ways. I might not be able to go back to x2, or I shouldn't be able to go back to x1 and x2. And if there's an edge, I sort of lose some edges. But if again, my minimum degree is high enough, I can keep walking safely. And you just repeat this as long as you can. And if you do a little bit of thinking for a moment, you can guarantee you can make it up to, xk. Once I reach xk, it's not clear I can go further. Because at xk, I may send all my edges back. I may send exactly k-1 vertices back, which is potentially my minimum degree there if I write this problem. I mean, you know, I stop when I've taken delta many steps, many edges walked along. Okay, so that's like a procedural way to argue it, but you just have to do a little more details. All right, so let's see if magically the spacebar works. Yeah, look at that. That's insane. So, all right. So let's do the cycle argument, because that one's kind of neat and actually very similar here. Actually, do we want to do that? Maybe we want to move on. We don't have a whole lot of time, so yeah, let's just do that one then. So we'll do connectivity next time. Okay, so the rest of the proof is for showing whether we have a cycle or not. Okay. Other idea. Yes. Okay. So for the cycle, I want to do the same thing. Take P is a longest path in the graph. So x1 and so on up to xk. This is x1. And again, because this is the longest path, all the edges of x1 go back into this thing, okay? Now, if I knew there was an edge from x1 to xk, I'm intentionally making that light, then I have a cycle of length delta plus 1, right? Because delta, we already showed, was at least k plus 1. But I don't know that edge exists. I know that they go back in. But basically, it does exist, because here's the thing. So let's look at xi, and let me define it here. So let I be largest index such that x1 xi is an edge. Okay, so that's like the longest cycle that we get from x1 onto this longest path here. There may not be any edge along here. I mean, any edge from here to this area, so I don't want to consider that. I just want to look at this cycle here, because this is definitely a cycle. And by the same reasoning, I want to argue that I is at least delta. Because if I is at least delta, then, wait, what do I want? I at least delta, or I want I minus 1 to be at least delta. Okay. Yeah, largest index there. So now let's look. The minimum degree of G is, again, bounded above by the degree of x1. It's better to say d of x1 is bounded below by the minimum degree, right? Obviously, it's at least the minimum degree. The degree of x1, though, is bounded above by what? x1's neighbors are all restricted to this piece here. They can only go to the vertices inside of this guy here by the definition of this one, right? That I was the largest I for which there's an edge here. So if there was an edge going to like here, then the I would be bigger, right? So all the edges coming out of x1 either go to these vertices or they could go out, but if they go out, it's a longer path. So I'm starting again with the longest path. So that means how many candidates for neighbors are there along this path from x1 to xi? How many vertices are available to be neighbors?
X sub I plus or minus 1.
Yeah, I minus 1, like quantity I minus 1, right? X1 is not adjacent to itself. I didn't say we were not working with a multigraph. In a multigraph, it's a different situation, although you're still actually okay. But it's at most I minus 1. So this actually gives a cycle of length. What's the length of this cycle that we see in this picture from x1 to xi and back? Yeah, it's I, right? There's I minus 1 along this path here and 1 more going back. So we have a cycle of length I, and the minimum degree is at most I minus 1, which means that I is at least minimum degree plus 1, right? Just solve this inequality here. So there's my longer cycle there, okay? If you think about these two for a little bit, you can actually combine the two together here. Maybe in the remaining minute here, can anybody tell me where we used? Did we use that the minimum degree of G was at least 2? Right? Either where did we use it or why was it important here? Because I didn't actually state it at any point here. Did anybody see that? Why was it important at this part of the proof?
It's our wraparound edge, like the one that when we close off, we're assuming it wasn't the very first edge we took out of x sub 1.
Yeah, that's right. Good, Van. Yeah, so up in this picture, P, drawing this edge here from x1 to xi, I assumed that there even was such an edge in order to get the cycle. Ordinarily, in the longest path, if your minimum degree is 1, you might have that x1's minimum degree is 1, and that's it. There's no other edges coming out of x1. And then it's like, well, how do I talk about this xi is the largest index such that it's an edge? You can also see it here. So I is the largest index such that x1, xi is an edge. This means that I is at least 3 because of the degree 2, right? Because it's definitely adjacent to x2 just by the definition of the path. But that wouldn't give me any type of cycle. So to get that I is at least 3, I'm using this minimum degree condition here to get that there. That'll give me this from degree of G, at least 2. But the path doesn't need that thing. However, if your graph just has minimum degree 1, then what does it claim about your longest paths? What's the length? What's the length? Not longest. What's the length of a path guaranteed in a graph of minimum degree 1? Just by the theorem, if you scroll up a little bit. It'd only be length 1, right? But that makes sense, right? If your graph, what's a graph of minimum degree 1 look like? It's like a bunch of edges that don't touch each other. Right? This graph, you can have graphs of minimum degree 1 with other higher degrees, but this is a conceivable graph you could have of minimum degree 1. And notice all the paths here are very short. They're all length 1 paths. So you can't guarantee more than that, okay? All right, anyway, that ends the proof of this longest path here. Next time we'll continue with connectivity, which is an important concept. It's all important.